All right, so yesterday we finished up talking a little bit about the E2 mechanism, and we said it's tricky. It's a concerted second-order reaction where the rate is dependent on both the concentration of your base and your substrate. We said anytime you do E2 chemistry, you have to identify beta protons, and then in addition to that, we said beta protons must be anticoplanar, meaning they must be lined up. It reminds me of dominoes falling over. If you're playing dominoes, right, you have to line everything up to knock them over. If they're offset, they won't fall over correctly. So in this case, we gave an example of cyclohexane, and we said with cyclohexane E2 reactions, your leaving group must be axial, and your beta proton must be axial as well for the E2 to occur. So let's take a step back and talk about reactions that don't involve ring systems, but are still E2. So I'm going to do a simple one first, and then we'll go to harder ones. And I'm going to color code my protons. I'm going to make this shorter. Okay, I've got a blue proton right here. I've got a green proton right here. I've got a red proton right here. I've got a leaving group that is a wedge, and an alpha proton I'll show as a black dash. All right? What we need to do is first identify which of the beta protons are anticoplanar for this conformation. So the way I like to do this is to draw a Newman projection. Believe it or not, we're not away from those yet. So we're going to look down this bond and draw the Newman. Okay, front carbon, we should have the prongs, right? What will be sticking straight up? Yeah, the blue proton. All right, and then what about over here to the right? It would be the green one. Okay, so we'll fill that in. That means our red one's left over. All right, so we'll do the back position now. All right, we've got 3 different prongs coming off of that. What will be sticking straight down? R. Okay, that's pretty easy. All right, what will be up and to the right? Hydrogen, the black hydrogen. And that means our leaving group must be over here. All right, so now this makes it a lot easier to identify the anticoplanar beta proton. Which color will it be? Green, right? Exactly. So this and this are anticoplanar. All right, so when we do this E2 reaction, what we're going to do is take some sort of base. Typically it's a strong base, something with a negative charge, and we're going to pluck off that green proton. We're going to clamp down, and we're going to kick off our leaving group. All right, but now we've got 2 different options for our product, and we're going to consider both of these. We should have the red and blue proton left over, right? So the question is the red proton going to be trans to the R group, or is it going to be cis to the R group? It's a little bit tricky to spot, but I'll show you guys a good trick with the Newman projection. With the Newman projections, what I do is when I identify my anticoplanar beta proton, meaning the one on the opposite side of your leaving group, circle the remaining substituents like this, and then say these will be cis to one another. In your final product. All right, so for this conformation, which structure is going to be correct? The bottom left or the bottom right? So the blue proton needs to be cis to the black proton, so it looks like this one would be the correct product for this given conformation. In reality, that methyl group can spin around. It doesn't matter which one you pick, but this is a good example of how to identify anticoplanar beta protons. All right, so now let's do a little bit harder one. So what I want you guys to do is to go through the same process, identify the beta proton that's anticoplanar, and then check with your neighbor to make sure that you're getting the exact same products. What does D stand for again? Yeah, deuterium. It's heavy hydrogen, right? All right, and we've got a methyl group coming off here. And I'm going to abbreviate ethyl group as ET. We're going to treat this with a strong base as well. So I'll give you guys a minute to work on this, but what I would do is draw your Newman projection first, just like we did before. Determine whether or not the beta proton is anticoplanar. What if it's not anticoplanar? What should we do? Rotate it until it is anticoplanar, right? So you may need to do a Newman projection rotation to a correct staggered conformation where you have an anticoplanar proton. So I'll give you guys a minute to work on that. All right, let's try doing this as a class. So I'm going to do my pretend eyeball looking down this bond, right? So that's our alpha-beta bond. Pretend eyeball. There we go. All right, that means we have a cross in the front. What's going to be sticking straight up? Hydrogen. What's going to be to the bottom right? Ethyl. That means our methyl group must be over here. Then we have our back carbon. What's going to be sticking straight down? Deuterium. What's going to be up here? Hydrogen. And if we look at bromine, it's got to be right there. So I'm seeing a problem right now. That's that we don't have an anticoplanar beta proton, right? So what I'm going to do is keep the front carbon static, and we're going to rotate our back carbon until we find an anticoplanar conformation. All right, so keep the front carbon exactly the same.
Why move the back one and not the front one?
You can move either one. It honestly doesn't matter as long as you find an anticoplanar conformation. That's a good question. Okay, so now let's do that. I'm going to move things around. So now let me kind of show where I'm moving this. I'm going to move this bromine down here. That means the deuterium's moving up here, and the hydrogen's moving over where the bromine was. Okay, so we've got a hydrogen here, we've got a deuterium here, and now we've got a bromine right there. So now we can quickly identify, hey, we've got an anticoplanar beta proton to that bromine now that we've done that sigma bond rotation, right? Okay, just like before, I would say, all right, that means in our final product, these will be cis in the product. But what I'm going to do is I'm going to redraw our starting material using this conformation. And so like I said, we essentially created a sigma bond twist. The front carbon we kept the same, so I'll draw it exactly the same. Now our bromine's down here. What's going to be coming off the wedge again? Hydrogen. And that means what's going to be on the dash then? Deuterium. Okay, so now can you guys see we've got these lined up in the same plane. They're anticoplanar. We're good to go. All right, so now let's apply our strong base. Got our strong base with the negative charge. This base is going to, grab this proton, clamp down like dominoes, and kick off our bromine all in one fell swoop. Now when we look at our final product, on this side we're going to have an ethyl group kind of sticking back. That's going to be cis to the deuterium, so the deuterium must be on that same face. And then we also have a methyl group coming off here, and that's going to be cis to that hydrogen. So for this reaction, we're only going to get one product. We're not going to get a mixture of different products. We have to do that sigma bond rotation in order to determine which product we're going to get. Does that make sense? Yep.
I was going to ask, would you expect to see the step of like the rotation of the 3D structure?
If it helps you, you can do it. If you can figure it out without doing that, that's fine too. I just really like to show it this way so people can see that, hey, these sigma bonds can rotate, and sometimes you need to rotate them to find that anticoplanar beta proton. It's not always cut and dry. All right, so quick question too. Is this isomer the E isomer or the Z isomer? See if you can figure it out and check with your neighbor. How many of you think it's Z? How many of you think it's E? How many of you aren't voting? All right, let's just pick one carbon. All right, so this one in blue, right? That's the left carbon. What's going to be higher priority, the deuterium or the hydrogen? Deuterium, it's heavier. All right, so I'll say higher priority up here. All right, then we'll look at this other carbon coming off the alkene, the green one. What's going to be higher priority, an ethyl group or a methyl group? Ethyl. All right, so they're on the same side, so will this be E or Z? Z. So for this E2 reaction, only the Z isomer is observed. You don't observe any of the E isomer. So we'll talk more about that in a little bit. Does that make sense? We do need to bring in some new terminology that you might see in your textbook, so I've got to define a few things. The first term is stereospecific. And if you're specific about something, does that mean you want one thing or that you're kind of flexible? You only want one thing, right? So a stereospecific reaction means you're only getting one stereoisomer out of the reaction. So the key word here is only one. All right, then we also have a different term called stereoselective. And stereoselective and stereospecific sound similar, right? But if you're selective about something, that's like going car shopping and saying, I want a sedan, right? It could be a Honda, it could be a Toyota. I just want a sedan. I'm selective about a sedan over buying a pickup truck, right? So selective means you can get multiple of the same things. So it varies. It's a reaction that gives an unequal mixture of stereoisomers. And let's make a note of that. What are the two different types of stereoisomers that we might run into? Enantiomers and diastereomers, right? They're connected in the same way but have a different 3D layout. So we'll write a mixture of enantiomers or diastereomers. Okay, and then one last term. This is regioselective. A regioselective reaction, do you think it's going to give one product or a mixture of products? Yeah, it's going to give you a mixture of products. Slightly different than stereoselective, though. In this case, your products aren't stereoisomers. They're going to be constitutional isomers. So again, the key word is an unequal mixture. That means selective, not specific. Specific means you only get one product. Some chemists will even take this further and add a couple other terms. enantiospecific and enantioselective. What do you think it means if something's enantiospecific? You only get one enantiomer, right? If it's enantioselective, what do you think that means? You get an unequal mix of enantiomers, right? So maybe you get a little bit more R than S. So you may occasionally see those terms as well, but these are the three main ones that you will run into in the Klein textbook. All right, so now let's go back and take a look at this reaction. Is this reaction stereospecific, stereoselective, or is it regioselective? Yeah, stereospecific, right? We're only getting one product out of this reaction, so it's a stereospecific reaction. It's not going to be stereoselective. That would imply we're getting more than one product out of it. Due to the nature of only having one beta proton, we're only going to get one product out of this reaction. So it is kind of a semantic thing, but it's important terminology we need to know when we're discussing reactions. Does that make sense? Okay, so now let's do another one. All right, for this reaction, I'm again going to use deuterium. I'm going to have a methyl group coming off here. I'm going to have two protons on this position. One I'm going to label as green, and one I'm going to label as blue. And then back here I'm going to have a leaving group. I'm just going to pick bromine. That's going to be a wedge, and then a hydrogen is going to be a dash. All right, so what I want you to do is to determine which proton is anticoplanar and whether or not you can twist it to have more than one anticoplanar beta proton. So let's take a look at the Newman projections. And so I'll give you guys a minute to draw both Newman projections where you have anticoplanar beta protons. So I'll call this Newman number 1 and Newman number 2. I might actually change one thing. I hope this doesn't mess up your notes too much. Let's change the deuterium to a methyl group. So just cross out your D and write in Me. I know it's going to make your notes less pretty. They weren't pretty before. Is that what you said? Like I write in a crayon. All right, let's try Newman number 1. All right, what's going to be sticking straight up if we're looking down, let's say this way? Methyl, okay. What's going to be to the bottom right? Hydrogen, what color? Blue? That means our green one's got to be back here, right? All right, back carbon, we've got 3 prongs coming off of it. What's going to be to the top right? Hydrogen. That means the bromine's got to be over here, and our methyl group's got to be down here. So if we look at this, this bromine's got an anticoplanar blue proton in this conformation. Are there any other protons that could theoretically be anticoplanar? Yes. Okay, so let's rotate it. So again, what I'm going to do is, it doesn't really matter if we rotate the front one or the back one. Maybe I'll keep the back one the same and rotate the front one this time. So if we keep the back carbon the same, all of the back positions are going to be in the same positions they were in. All right, this time what I'm going to do, though, is I'm going to take this green proton, slide it over here. I'm going to take the blue proton, slide it over here, methyl group, slide it where that green proton is. Does that make sense? So now we've got a methyl group down here. Blue proton's going to be up top, and green proton's going to be over here. All right, I'm going to erase this just for clarity's sake. So we've got two different conformations where we have an anticoplanar beta proton, right? Either the blue proton can be aligned so that it's anticoplanar, or the green proton can be aligned so it's anticoplanar. All right, so now the question is, which of these conformations is more stable? First one's more stable. Why is that? Yeah, exactly. So this is the more stable conformation. This is less stable. And we know that this is less stable due to this methyl-methyl Gauss interaction that we saw earlier on in the year, right? Okay, so now what we need to do is to, again, circle our groups to determine which are going to be cis to one another. We know the methyl and hydrogen will be cis here. Methyl and the green hydrogen will be cis there. And then down here we'll have another grouping of cis groups. All right? So what I'm going to do is kind of redraw these a little bit, and I'm going to say, all right, this is Newman 1. Whoop. And with Newman number 1, we're going to have a bromine back here. We're going to have a blue proton right here. And now we need to kind of transcribe this, right? So the methyl group would be coming off this position. Our green proton is going to be sticking up here. And then in the back, we're going to have a hydrogen down here and a methyl group right here. So the main thing to pay attention to is we haven't changed the stereochemistry, right? Can you guys see that? It's a little hard to spot. And what we'll do is draw our base with the negative charge. And we know in this case, this proton is anticoplanar to that bromine. They're both in the same plane. So what we're going to do is specifically target that proton, clamp down, eject off our bromine, and we need to draw our final product. So we know we're going to have some sort of central carbon-carbon bond. We know the methyl group's going to be sticking off here. What will be cis to it in this position? If we go back up and we look at it, right, the methyl group's got to be cis to that black hydrogen. So I'll draw that in. All right, and then the methyl group off of the left carbon's got to be cis to what? The green one, right? All right, so that's the product for Newman projection number 1. All right, let's do the same thing for Newman projection number 2. So Newman projection number 2, we've got a bromine that should be anticoplanar to this green proton now. We still have a methyl group here. We have a hydrogen here. We've got a methyl here, and we've got a blue proton there. So same thing, we're going to take a strong base. The strong base this time is going to target the anticoplanar green proton. Grab this, clamp down, and eject off our bromide. All right, so same thing. We're going to make an alkene with 4 things coming off of it. The carbon on the far right-hand side has to have a methyl group coming off of it. And what's going to be cis to that methyl group for Newman number 2? Methyl, right? Because if we go back up here, we said those 2 methyl groups are on the same side in that Newman projection, so they've got to be cis to one another in the product. So if we go back down, this methyl group's got to be cis to this methyl group. This black hydrogen's still there, and we've got a leftover blue proton. All right, so when we look at this, we will get two products. All right, do you think we're going to get these products in an equal mixture or in an unequal mixture? Unequal, right? Because when we went back up and we looked at our Newman projections, we said Newman number 1's more stable. That's going to be present at a higher concentration under normal conditions than the less stable conformer. It doesn't like being in that position. So if we look at it, the product from reaction number 1 is going to be major. So let's label that. And down here, it's going to be minor. So we'll label it this way. All right, so now going back to our terminology questions. All right, if we're getting two different products, is this going to be selective or specific? Selective. Is this going to be regioselective or stereoselective? So how are these related to one another? Exact same connectivity, right? We have a methyl group coming off of each side of an alkene, but different 3D layout. What would we call that? Diastereomers. So let's make a note of that. Get an unequal mix of diastereomers. So will this be stereospecific, stereoselective, or regioselective? Stereoselective. So there are some E2 reactions that are stereospecific based on the nature of the beta protons, meaning you only have one. And then there are some where it's specific or selective, meaning you've got multiple beta protons to select from, but you might not get an equal mixture of products out of it, right? It's going to be an unequal mixture. So this would be a good example of a stereoselective reaction. Does that make sense? Yep.
Is the major are the major and minor products determined based on the stability of the Newman projection before the reaction always, or is it also a factor of their stability after?
That's a really good question. So Rachel was asking, does it have to do with the stability of the Newman projection or just the stability of the product, right? Because we know that trans products are more stable than cis products. That's always going to be the case. But we also know that the reaction rate is always going to be determined by concentrations of things. So in this case, it has more to do with the fact that the more stable conformer is going to be present at a higher concentration. So it's going to be the faster reaction and outcompete the slower reaction. So it's kind of two sides of the same coin. It's a little bit tricky that way. And I know this can kind of make your head hurt with the 3D rotations and stuff like this. Again, this is a type of problem where I really like to pull out a model kit and actually physically rotate it until I find that anticoplanar beta proton and then lay it on its side and then transfer it into a 2D drawing. It can really make your head hurt trying to do it otherwise. So if that works for you, go for it. All right, you guys want to try a hard problem? Oh, we'll talk about these guys later. Old bearded white men. So when R2-bromobutane is treated with a strong base, you get three products. What are they? So this would be an example quiz or exam question, but I'll give you guys a minute to work on this. So let's maybe start by drawing our starting material. Butane is how many carbons? 4. I'm just going to number going this way because I can. All right. I'm going to put bromine off of here just as a wedge. We'll guess and check and see if we're right. So I've got bromine on there as a wedge. Let's check to make sure that it's actually R and not S. Highest priority will be bromine. What will be higher priority? The ethyl group, meaning carbon 3, or the methyl group, meaning carbon 1? Okay. So it'd be 2 and 3. We rotate around. Is that R? Yep. So we're good to go. We don't need to flip it. So this would be our starting material, and it's saying if we treat this with a strong base, we're going to get 3 different products. And what will those products be? Give you a hint. We already did this problem and we solved 2 of them, but we're missing the 3rd. So what was our product that we got from the last one? We got 2 diastereomers, both cis and trans, right? So let's take a look at that. We said, all right, when we have 2 protons coming off here, this proton is anticoplanar to that one, right? So it's a dash where it's a wedge. We'll grab that, clamp down, kick that off. All right, and then we're going to get a methyl group here. We're going to get a methyl group here. We're going to get a hydrogen, and we're going to get a hydrogen. We'll do the same thing, but with a different proton. All right, so if we do this, we could say, all right, we're going to rotate it so that the methyl group is now down here. We've got 2 hydrogens. And we've got a bromine right here. I'm just going to fill these in with methyl groups too, so we're keeping track of everything. All right, so strong base in this reaction, like we just saw, we'll grab this anticoplanar beta proton, clamp down, and we're going to get cis products. What's the 3rd one coming from? What's that? Protons on the methyl group? Exactly, right? We've got more beta protons than just those 2. So let's draw that out. That methyl group over here is still beta, right? We've got all of these protons down here. Sorry, my pen's glitching up. So draw the product you would get if you deprotonate one of those beta protons. Oop. So we grab one of these beta protons, clamp down, kick off our leaving group. Does it matter which one of those beta protons we select? No, it doesn't matter at all. So this would be our 3rd product. All right. Now the ultimate challenge question. Which one of these is going to be the most major product, second most major product, and third most major product. And let's assume our base is pretty small and that it can go after any of those beta protons, and it makes no difference which one it goes after. What do you guys think? Top one's most stable? Why do you think the top one's the most stable?
Methyl groups are facing away from each other.
So is it mono, di, tri, tetra substituted? How would we classify the top alkene? How many carbon groups are coming off the alkene? 2. We've got 2 methyl groups, right? So that would be di substituted. The middle one there is also di substituted, right? But which one's more stable out of the top 2? Top one, because it's trans. So this would be trans, di substituted. This would be very stable. This would be cis di substituted. This would be moderately stable. And then what about the bottom one? How would we classify it? Would it be mono, di, tri, tetra? Mono substituted. Would it be cis or trans? Or neither? For this bottom one. Can we classify it as cis or trans? No. So in this case, we would just say mono substituted. And this would be our least stable product. So what we'll do tomorrow is we'll talk a bit more about E2 chemistry. The base that we choose can also impact your products as well, but it's a little bit overwhelming to absorb all of that in one day, so we're going to cut that into the next lecture day. I know this stuff can be tricky. I really recommend with this next problem of the day that you work with a group. Try to do the Newman projection rotations kind of like we did in class, and try to get a jump start on it. Don't leave it until right before class, because it may take some time.